Okay, today we're going to be talking about doing an obstacle avoidance version using the same two chips, the IR sensor and the dual H-bridge motor driver. In this case, it calls under a lot of different numbers, but L298N would be one of the more common ones. You can find both of these very inexpensively if you do a little bit of searching, under $1 each. Using the TT gear motor, 148 gear ratio, and just two AA batteries as a counterbalance. See, there's a little bump that you glue on the bottom of this main frame prints as one piece, and the batteries hold it on that bump so that the front is floating so that it can spin real easily. If you watched my edge detection non-fall one, you'll see the complete explanation of how this one-way wheel, one-way bearing is being used as a wheel with an added ratchet so that it locks up right away so it'll spin in place. I did a short video showing this running in a large contained area. I'll put a link to that, so you should watch it. We can run it here, but this isn't a very big area. But if you haven't watched that one, it's probably better than nothing. But the long and the short of it is, this sensor right now is showing it has power, and this wheel and this wheel are both driving forward. If it was on a surface, it would be moving that way. But as soon as this sees something, now they've reversed. And you see this wheel has stopped turning, but this one reversed. So that's going to make it rotate rather quickly. Let's just do this. I'll put my hand down here. This board isn't really big enough for any sort of a demonstration, but this is the work area we're in. So, I suggest you watch this short video showing this in a large area with the wall containment and everything. The schematic for this is rather simple. Both devices are going to be fed 3 volts. You have a positive and negative and the control out on the IR sensor, and on the dual H bridge you have a positive and a negative input. So again, I'm giving them both the 3 volts, and this H bridge motor driver is wired in a special way so that a single control line, which is this line right here, can reverse the motor direction. Normally you have to have 2 control lines to reverse the motor direction, but by taking this top output B and bring it into pin 4, which is an input, and then bridging pin 3 and pin 2 together as our new control line, and tie pin 1 to V+, you can use the second half of that dual H-bridge driver as an inverter so that a single control line can make the motor change directions. It's very simple, doesn't require any other parts. Now, once this has detected something, in this case, the output of this IR sensor is going to go low. Normally when it doesn't see any reflection back, it's at a high state. But when it does see reflection, it goes low. Well, I wanted this to work on the same principles as the edge detection non-fall one that I just did, so that in fact, in the end, we could tie the two together. We could put the edge detection one in the front so it can't fall off steps or off tabletops, and have the IR sensor. So I'll be doing a video on that shortly. But the point is, I wanted them to work in the same way so that they could be tied together. All I'd have to do is add another sensor. So what I'm taking is this output, when it goes low, through a current limiting resistor, 10K resistor, and I'm going to use a PNP transistor. Any standard PNP here in America, one of the most common is the 2N3906 PNP. It doesn't have to be able to source any major current or voltage or anything like that. You got your PNP, take your emitter, tie it to the 3 volt line up top, take the collector, tie that to the control line, and then the 10K current limiting resistor from the control line of the IR to the base. So anytime this line goes low, that's going to force this collector, which is normally an open circuit, to become V+. And that V+ is going to reverse the motor direction, and it's going to charge this capacitor. You can see one side of the cap is tied to ground, the other side's on the control line. This is a 10 UF capacitor. Now, once this does no longer sees the reflected back and this goes high, this transistor goes back into an open collector state. where it's not doing anything. So you're going, well, okay, what's going to discharge this capacitor? Well, the inputs on this dual H bridge have internally built pull-down resistors. And I can't remember the exact value. I seem to think it was like 10K, but it could have been something else. I don't remember. And it doesn't matter. Point is, those pull-down resistors on these input pins are what's going to discharge this capacitor until this goes back low. And once it goes low, then the motor is going to reverse. We need that little bit of a delay time, so when it senses something, the motor stays reversed long enough for it to head off in a new direction without any sort of pulse with expanding capacitor here changing that. It would be so instantaneous that the second it bumped away, it'd be like a vibrator. It'd just be going back and forth, and it wouldn't be able to turn away. So you need to add some delay time so that it has time to turn away. All of these files are up on Thingiverse, and in fact, since there's so few parts to print, they all fit on one plate. Like on an A1 Mini, you can print the whole thing, because basically you have this frame, which is the only this frame, and I do supports on the inside where this motor's sitting. I use tree supports in there because they're easiest to break away. So when you print the part, you can snap all those off. This little nubbin that you just glue anywhere on the back here, that's a separate part. The clutch wheel is made up of 3 parts. There's this outside ring, there's an inside ring, and then there's the hub that goes onto the motor shaft, which I hold on with a long number 2 screw. The separate little ratchet arm prints as one piece. No supports. I'm using a nail in this case just to hold it on there. Whatever you use, it just has to hold it on there loose so that gravity will allow that to drop down and lock up. The wheel on this side, it prints as one piece because it drives all the time forward and backward. And that's pretty much it. There's not very many parts. It's very simple to assemble. If you use the switch, I'm using my standard slide switch I like to use, which has mounting holes on 19mm centers. And it's just going to break the battery connection, the positive connection, in this case. I can't think of much else. There's a provision. See a little teeny screw down in there? That's a short number 2 screw. I had some number 2s at 6mm long. 4 would have been better. And there's a place in this plastic where you can just screw it down and it locks it in place. And there's a hole provided in this where you can take another number 2 and screw this sensor in place. And that's pretty much it. You can see the only modifications to invert the signal. Well, I was going to talk about that more. You know, I'm using this transistor to basically change the output, which goes low when it sees something reflected, to going high, which was the point of the PNP transistor. You could do it all on board here if your eyes and your soldering guns are small enough, because the chip that they're using here is a comparator chip, but it's a dual comparator chip, and they're only using 1/2 of it. The other half of it, all the 2 inputs and the output, are left unused. So if your eyes and your soldering tip gun were small enough, you could tap into the second half of that chip and wire it as an inverter, so you could get a positive out when it sees the reflection and a negative when there isn't any. But it's just too much for me at this point with my eyes and my large soldering gun to do that. So I decided just to throw a transistor on externally. They're so inexpensive, and the resistor, 10K is so inexpensive that why not do it externally? Okay, I think that's it.